Hello everyone. During the last lecture we start explaining what voltage and current in electrical components are, and we explain why those two are actually important for us. Just to recap, the voltage is the electrical potential difference across the component, and the current is the passage of the charge per unit of time through the component. And with those definitions, so again, the voltage is the potential difference across, or in other words, we take the energy and derive it with respect to the charge and define voltage, and then the current is the charge passing through a cross-section in the device with respect to the time. And we said if you take these two and multiply them by each other, you get as a result derivative of energy with respect to time, which is by definition power. Okay? And therefore this is a very useful way of defining variables in the domain of electrical, since we can, using these definitions, we can simply calculate the power in each electrical components by just taking these two variables and multiplying by each other. Just to make sure that we don't lose touch with why any of these discussions are important, let's review the fact that all devices, all machines that we use are designed to help us do work, basically useful work. And the way that we do that is that the system, the device, inputs, there's energy coming into the system, and using that energy, the device turns that energy into useful work. And that's true for any of the devices and machines that you can imagine. Now, in the electrical domain, the way that the kind of energy that you input is electrical energy, and then that electrical energy can turn into a useful work one way or the other. For example, in the case of a light bulb, which we mentioned earlier on, you input electrical energy, and that energy turns into light and heat, obviously. And and by the way, this is an old incandescent light. Lighting technology is different these days, but that's a topic for a different time. So electrical energy enters the system, and that energy turns into some kind of energy or work that is useful for us. In this example, the light that comes out of the light bulb is important and useful for us. And you can extend this to any kind of other application or other device or electrical machine. So now, what is important really to understand is how much energy or power is coming into this device, and how is that energy turning into a different form of energy, and what percentage of that energy is actually the useful work that I'm looking for. Which, by the way, the useful portion of the energy, in this case, the light that is coming out of the system, divided by the energy that is given to the system, is a lot of times defines the efficiency of the system. So useful work, useful power, useful energy divided by all the energy coming in actually is the efficiency of the system. Now, how do we inject energy or electrical energy into the device? We usually connect it to a source. How do we make sure that the source can actually inject energy. We basically, at the core of it, we take a positive and negative charge and make sure that we can separate the two from each other. Once we separate the positive and negative charge from each other, immediately you're going to get force or electrical energy in the form of a potential energy conserved in the system. And once you connect this to your device, that energy could then be delivered in the form of kinetic energy, which is the movement of the charged electrons in this case through the system. And each one of the electrons or the charge that is passing through the system carries energy or kinetic energy with it, and that kinetic energy could be turned into any other kind of useful fork in the system. So these sources, let's say we can assume that, for example, this is a battery, right? So that's the positive and the negative. And then now you connect that to your light bulb, and then through passage of electrons, electrons go this way, and the current, as we explained, the current actually goes in the reverse direction of the electrons. So charge passes through the system, and the kinetic energy, the potential energy, turns into the kinetic energy that is associated with the movement of the electron through the circuit, and that kinetic energy turns into useful work for us. Now, how much energy or how much power is being delivered, how much of that power turns into useful work, these are the most fundamental and important questions for us. Now, that said, we kind of know how to do it now. We take this and symbolize it with a box. We say, okay, if I can measure the voltage that is across this, and then measure the current that is passing through it, and then multiply the two by each other, I can tell you how much power is being delivered to this device. And that's true. I guess the questions, some of the questions that could arise here is that, great, this is how we define the voltage and current, and based on the definition we can calculate the power, but how do we actually measure the voltage and the current? Which are really good questions that I encourage you to look for the answer for those, and we can actually discuss some of that in class too. That aside, let's look into calculation of the power in more detail and define some conventions. This is an important discussion. So, let's move on to this figure. As you can see, in these different four different cases, you have these electrical components, and in each case you have defined a voltage that is the potential difference between where you put the positive subtracted from where you put the negative. So the voltage across this is the voltage or potential of terminal 1 minus the potential of the terminal 2. And that's different from this one in a sense that the voltage here is the potential of terminal 2 minus the potential of the terminal 1. Okay? And also the direction of the current, in a sense, in each one of these cases is different. For example, in this example, the current enters the terminal 1 and it comes out of the terminal 2, whereas in these two cases the current is actually entering terminal 2 and coming out of the terminal 1. So with that we have four different cases. We have the first case where the voltage is defined as terminal 1, potential terminal 1 minus potential terminal 2, and the current goes from terminal 1 with the positive potential to the terminal 2 with the presumption that the potential is lower. Now with that convention, if this is how the definition of this is how the current and the voltages are defined, to calculate the power, you take just simply the voltage that you measure and multiply it by the current that you measure, and that would give you the power in the system. But that's not the case if you have a situation like this, where the current actually enters the terminal with the potential of that is assigned a negative sign, meaning that the presumption is that that's the lower potential. So if the current is entering to the terminal with the negative sign, then the power that you define is actually not simply the voltage that you measure multiplied by the current, and rather it's the voltage multiplied by the current and then multiplied by a -1. So you take that value of the voltage, take the value of the current, multiply them by each other, and then negate that, and that would be the power. This is just a convention, and we explain why that matters. Again, in this case, which is very similar to that case, the current is actually entering the potential that has a negative sign assigned to it. So you take the voltage and current and negate that. In the last case, the current is entering terminal 2, but that has a positive sign assigned to it, so it goes back to what it was originally defined. Just take the value of the voltage, take the value of the current, and multiply it by each other, and that would be power. So what's important is to note which one of the terminals, negative or positive, the current is entering into. Okay? If it's entering into the terminal with the positive sign, then you just take the voltage and multiply by the current. If the current is entering to a terminal with the negative sign, you take the voltage, multiply by the current, and put a negative sign beside that. In other words, negate that value. Okay, so that said, let's make sure that we understand why this mattered. So what does it mean for a power to be positive or negative? So the unit for power is volt amp, because the unit of voltage is volts and the unit of the current is amps, so the unit of the power would be volt amp. In other words, the unit of the power is basically energy per unit of time. The unit of energy is joules per second. So the other way to say volt amp is joules per second. Now, when you do the calculation, if at the end the value that you calculate has a positive value, that based on this convention, what it physically means is that this component is actually consuming the electrical energy. So what does energy consumption means? It means that the energy in the form of electrical, in the domain of electrical, comes in and actually turns into a different kind of energy in this component. So the energy gets consumed. A good example of that is again that light bulb that we explained. So the energy in the form of electrical comes into the light bulb, but then it actually leaves the light bulb in the form of light and a lot of heat. So electrical energy comes in, heat and light leaves the system. So the light bulb consumes energy, electrical energy. And if you take the voltage and multiply by the current, that value comes out to be a positive number. So whenever you get a positive number as a result of this calculation, that means that your component, your electrical component, is actually consuming or using that energy. Now, if the result of that calculation becomes a negative number, that means that that component is actually generating electrical energy. What does that mean? That means that it actually takes some other form of energy and turns it into an electrical energy or electrical potential. An example would be a battery. So in the battery, the electrical energy actually doesn't come in, it leaves the system. So this battery generates electrical energy and outputs it to the light bulb in this case. So let me redraw it because this is the light bulb. So once you calculate the power for these two, the power, I'm going to call it the power of light bulb, is going to end up being a positive number, whereas the power for the battery is going to end up being a negative number. The positive power means that the light bulb is consuming electrical energy, and the negative power for the battery means that the battery is generating electrical energy. And that's according to the convention or the way that we define the current and voltage in our devices. That's an important concept that we're going to use quite frequently in this course and in circuit analysis generally, or circuit design. So let's go to this example in the book. This is going to actually be quite useful to solidify what we are discussing here. Let's say we have 8 different electrical components that are connected to each other in a network that looks like this. Now, we know that within this network, for any kind of energy to be dissipated or transferred from one source to the other, we have to have components that generate that energy, and we have to have components that consume that energy. If none of these components that exist in this network generate energy, obviously you don't have any force that pushes charges around, and therefore nothing is going to happen. And you can be sure that none of these currents are going to have any value. So you have to have energy stored in one of these components, one way or the other, so that that energy gets delivered to the rest of the system. Now, it could be one of the components, it could be more than one of the components that generate. We don't know what these components are. Any one of these components could be batteries or power sources, electrical power sources. Now, given that, if we know that there is going to be some action going on in this network, this system, in terms of the energy, electrical energy, is isolated from the rest of the world, meaning that there is no other electrical connection to this network. So if there's any energy coming into the system, is coming from these components, and therefore any generation and consumption is basically is all held within the system. Now, we know that the energy doesn't come from nowhere and it doesn't disappear. So all the energy that is generated within this system does have to be confined within the system, meaning that the energy that is generated is going to be consumed. So if I calculate all the energies or powers that are generated by the components within the system, and then calculate all the powers that are consumed by all the components within the system, and add them up by each other, it's very intuitive to assume that the total power has to end up being 0, since there is no interaction, electrical interaction with this system from outside. And that's one way to calculate the distribution of power within a system, to use the zero sum of all the powers as a rule for the analysis. So then again, if I start basically labeling the circuit and assuming certain direction for the currents that are passing through the components, and assume voltages across by putting positive and negative sign, I can start calculating the power for each one of these components. So let's try that and practice the convention that we defined earlier. Okay, so starting from the component A, I'm going to call that PA, the power for component A. So the current is actually entering the positive terminal, so that would be therefore simply the voltage across multiplied by the current that is passing through it. Make sure that you follow me in terms of how I explain these parameters. The voltage across and the current passing. Okay, voltage across, current passing through. Now PB for this component. Now for this one, the current is actually entering the negative terminal, so which means I'm going to have to multiply that by a negative sign. VB, then IB. Then let's just keep doing that for all of these. IC entering the positive terminal, so it would be VC times IC. PD entering negative terminal, minus VD. ID. PE entering the positive terminal, that would be VE, IE, PF, entering the negative terminal, minus VF, IF, PG, entering the positive terminal, VG, IG, and last, PH, entering the positive terminal, so VH, IH. Now, if I take all of these and add them to each other, so sigma P I going from A to H, this has to be equal to 0. Why? Because this system is isolated from the outside. There is no electrical connection between these components and outside. So no electrical energy can enter or leave in this system. And since we know energy doesn't disappear, energy doesn't come out of nowhere, all the energy that is produced in this system, generated in this system, has to be consumed by the system. So you take all the powers, which is energy per unit of time, add them up, and then that has to be equal to 0. Now, the book has a table for all of these values, and if you take these values and do this calculation, and you end up meeting this this criteria, then that means that all of these definitions that we have here, the values that we have measured, are correct. If this is not the case, then you have made a mistake in your measurements, and that needs to be corrected. Okay, this is an example, a simple example that might be useful, and you have some experience with that when one of your batteries actually in your car, and if your car runs for whatever reason the battery is dead, you can't start the car, and you can use a battery from a different car that is functional to recharge it for at least a short while. In this case, one of the batteries is actually generating power, and the other battery is using the power. So if you notice, assuming that it's the red car that is still functional and the blue car is not, the current is coming out of the positive terminal and going into the positive terminal of the blue battery. So going into the positive terminal means that whatever that current is multiplied by the voltage across it is the power that is actually delivered to that or consumed by that. And this one is actually generating the power. So the current goes into the negative terminal. So if you calculate the power for this one, you're going to end up seeing a negative value that is exactly equal to the value of the power that you calculated for the other one. This one negative, that one positive. This one is generating the power, the other one is consuming the power. So this is just an example to show you that even a battery that is traditionally presumed to be a device that generates electrical energy in a certain situation could actually consume electrical energy. For example, when you're charging it. When you're charging the battery, it's actually consuming. The energy comes in and gets conserved in the form of potential energy in the battery. That said, we're going to end this lecture with what we covered so far. I can actually start assigning you homework from chapter 1. Make sure that you start doing the homework and come to face-to-face sessions with questions from the homework or any other topics that were discussed. Thank you, and I'll talk to you in the next lecture.